You know, there's something deeply unsettling about realizing that one of the most fundamental aspects of your daily experience, the relentless flow of time, the sensation of moving from past through present into future, might be an illusion. Not an illusion in some vague philosophical sense, but an illusion in the same way that the apparent motion of the sun across the sky is an illusion. The sun doesn't move around Earth. Earth rotates. Similarly, time doesn't flow. We exist in a static four-dimensional structure, and the sensation of flow is an artifact of how our consciousness processes information. I want to take you on a journey through what modern physics tells us about time, because the picture that emerges is radically different from our everyday experience. And I mean radically, not just surprisingly different in details, but fundamentally different in character. Time, as physics describes it, bears almost no resemblance to time as we experience it. The flow, the now, the distinction between past and future, the feeling that the future is open while the past is fixed, none of these features appear in our fundamental equations. They're not part of the deep structure of reality as we understand it. Let me start with what seems like the most obvious, incontrovertible fact about time. It flows. Right now, you're experiencing this moment, this present moment, this now. A moment ago was different, that was the past. A moment from now will be different, that will be the future. And you're moving through time from past to future, like riding a river that carries you inexorably forward. You can't stop it, can't slow it down, can't reverse it. Time flows and we flow with it. Except, and this is where physics starts to undermine our intuitions, there's no evidence for this flow in the fundamental laws of physics. When you write down the equations that govern how the universe works at the most basic level, there's no now, no present moment moving through time. There's no flow. There's just a four-dimensional structure, a block universe, as it's sometimes called, where past, present, and future all exist equally, eternally, unchangingly. This is what Einstein's theory of relativity tells us, and it's not speculative or controversial among physicists. It's been confirmed through countless experiments and observations. Let me explain what I mean, because this is crucial for understanding the true nature of time. In relativity, space-time is a four-dimensional entity. 3 dimensions of space, forward, backward, left, right, up, down, and 1 dimension of time. These 4 dimensions are interwoven into a single geometric structure. Events in space-time have locations in all 4 dimensions. They happen somewhere, 3 spatial coordinates, and somewhen 1 temporal coordinate. Just as a location in space requires 3 numbers to specify it, a location in space-time requires 4. Now here's the key insight. In this 4-dimensional space-time, all moments, past, present, future, exist in the same way that all locations in space exist. Consider spatial distance. New York and Los Angeles both exist right now, even though you might be in New York and Los Angeles is far away. The fact that you're here and not there doesn't mean there doesn't exist. It just means you're at a different location in space. Similarly, in the space-time picture, yesterday and tomorrow both exist, even though you're experiencing today. The fact that you're at this moment and not that moment doesn't mean other moments don't exist. It just means you're at a different location in time. Just as being in New York doesn't make Los Angeles any less real, being at this moment doesn't make other moments any less real. This is what's called the block universe, or eternalist view of time. All of space-time, all of history, from the Big Bang to the far future, exists as a single, unchanging, 4-dimensional structure. You and I are 4-dimensional objects, world lines, threading through this structure. Your world line extends from your birth to your death, and all moments of your existence are equally real, equally present in the 4-dimensional structure, even though your consciousness only experiences one thin slice at a time. Now, I can feel the objections rising. This seems to contradict everything we experience. When I say now, I mean this moment, this present instant, not yesterday or tomorrow. Those feel fundamentally different. The past is gone, fixed, unchangeable. The future hasn't happened yet. It's open, uncertain, not yet real. The present, the now, is what's actually happening, what's real right now. But here's the troubling fact. There is no universal now. This was Einstein's great insight, and it's been verified experimentally countless times. What counts as now depends on your state of motion. Events that are simultaneous for you that happen at the same time from your perspective are not simultaneous for someone moving relative to you. Let me give you a concrete example. Imagine you're standing still on Earth, and your friend is on a spaceship traveling at high speed. You both look at your watches and note that it's exactly noon. At that moment, you both think now it's noon and believe you're experiencing the same moment, but you're not. At least not in any absolute sense. From your perspective on Earth, there are events happening right now on a distant planet, say 10 light years away. You consider those events to be simultaneous with your noon, they're part of your now. But from your friend's perspective, on the fast-moving spaceship, different events on that distant planet are simultaneous with their noon. If the spaceship is moving toward the planet, events that are in your future are in your friend's present. If it's moving away from the planet, events that are in your past are in your friend's present. This isn't a small effect or a measurement uncertainty. It's fundamental to the structure of space-time. There is no universal present moment, no cosmic now that all observers agree on. Simultaneity, what it means for two events to happen at the same time, is relative. It depends on your motion. This relativity of simultaneity absolutely demolishes the common sense notion of time as a universal flow. If there's no universal present moment, then there's no meaningful sense in which the universe as a whole is at a particular moment and moving toward the next. Different observers divide space-time into past, present, and future in different ways. And there's no privileged division, no objective fact about which division is correct. Here's an even more striking example. Right now, as you're reading this, there are events happening on a planet orbiting a distant star. From your current perspective, with you sitting relatively still, those events might be in what you consider the present. But imagine someone else moving at high speed relative to you, passing by Earth right now. From their perspective, those same events on the distant planet might be in what they consider the past or the future, depending on which direction they're moving. This means that what counts as already happened versus happening now versus hasn't happened yet depends on one's motion. There's no absolute division of space-time into past, present, and future. These categories are observer-dependent, like left and right or up and down, just as there's no absolute fact about which direction is up in space. It depends on your orientation. There's no absolute fact about which events are now in time. It depends on your motion. And if there's no universal now, then in what sense does time flow? Flow implies movement from one moment to another, from past through present into future. But if these divisions aren't absolute, if different observers slice space-time into past, present, and future in different ways, then what's doing the flowing? What's moving? The block universe picture suggests that nothing is flowing. All of space-time just exists eternally as a four-dimensional structure. Your experience of flow, of moving through time, is an artifact of how your consciousness processes the information encoded in your world line. You're not moving through time, you're a static pattern in four-dimensional space-time that contains, encoded within it, memories of earlier moments and anticipations of later moments. The experience of flow emerges from the structure of that information, not from any actual movement. This is profoundly counterintuitive, and I don't blame you if you're struggling with it. Our entire experience is saturated with the sense of time flowing, of the present moment being special, of the future being fundamentally different from the past. How can physics tell us that this is all an illusion? Let me dig deeper into why physicists take this view seriously. Because it's not just philosophical speculation. It's based on our best theories and strongest evidence about how the universe actually works. First, consider the fundamental equations of physics. Whether we're talking about Newton's laws, Maxwell's equations for electromagnetism, Einstein's equations for gravity, or the Schrödinger equation in quantum mechanics, these equations are time symmetric, or nearly so. That means they work equally well running forward or backward in time. If you take a solution to these equations and reverse the direction of time, swap past and future, you get another perfectly valid solution. There's no arrow of time built into the fundamental laws. They don't distinguish between past and future, don't privilege one direction over the other. If you filmed fundamental physical processes and played the film backward, the reverse processes would obey the same laws as the forward processes. Now, you might object, but obviously time has a direction. Eggs break but don't spontaneously reassemble. Coffee cools but doesn't spontaneously heat up. People age but don't grow younger. There's clearly an arrow of time in the world we observe. And you'd be right, there is an arrow of time in the macroscopic world we experience. But crucially, this arrow comes from thermodynamics, from the increase of entropy, not from the fundamental laws governing individual particles. The second law of thermodynamics says that entropy, roughly, disorder, or the number of possible microscopic arrangements consistent with macroscopic observations, tends to increase over time. This gives us a direction. Entropy was lower in the past and will be higher in the future. That's why eggs break but don't reassemble, why coffee cools, why we age. These are all processes that increase entropy, that move from more ordered states to less ordered states. But here's the key point. The thermodynamic arrow of time is statistical, not fundamental. It emerges from the fact that there are vastly more disordered arrangements of particles than ordered ones, so systems naturally evolve toward disorder simply because there are more ways to be disordered. It's not that the fundamental laws favor one direction of time over the other. They don't. It's that given certain initial conditions, the universe started in a very low entropy state near the Big Bang. Entropy increases are overwhelmingly probable as you move away from those initial conditions in either temporal direction. The thermodynamic arrow gives us a direction we can call future versus past, but it doesn't give us flow. It doesn't give us a moving present moment. It just labels one direction through the four-dimensional space-time structure as the direction of increasing entropy. The structure itself remains static, eternal, unchanging. Moreover, the thermodynamic arrow is contingent on special initial conditions, the fact that the universe began in a low entropy state. If the universe had started in a high entropy state, or if we lived in an eternal universe with no beginning, there might be no consistent thermodynamic arrow, and yet space-time would still exist as a four-dimensional structure. The arrow of time is a feature of our particular universe, not a necessary feature of time itself. Now let me address another aspect of our experience that seems incompatible with the block universe, the apparent openness of the future versus the fixedness of the past. It feels like the past is determined, set in stone, unchangeable. What happened, happened, and nothing can change it. But the future feels open, uncertain, not yet determined. We make choices that affect the future but can't change the past. However, in the block universe picture, this asymmetry between past and future is also an illusion, or at least observer dependent. From the four-dimensional perspective, the future is just as fixed as the past. Your entire world line, from birth to death, exists in the space-time structure. Everything you will ever do is already there, just as everything you've already done is there. The future is no more open than the past. Both are equally real, equally determined by the structure of space-time. But wait, you might protest. Doesn't quantum mechanics introduce genuine randomness, genuine indeterminacy into the future? Doesn't that mean the future is open in a way the past is not? This is a good question, and it brings us to the relationship between quantum mechanics and time, which is complicated. Quantum mechanics does introduce apparent randomness into physical processes. When you measure a quantum system, you get a random result from a range of possibilities with probabilities determined by the system's wave function, but no deterministic prediction of which specific result you'll get. However, and this is crucial, even quantum randomness doesn't necessarily mean the future is open in any ultimate sense. There are interpretations of quantum mechanics, like the many worlds interpretation, where the apparent randomness is just an artifact of our limited perspective. In the many worlds view, all possible measurement outcomes actually occur in different branches of reality, and the wave function never collapses. It evolves deterministically according to the Schrödinger equation. In this interpretation, the complete quantum state of the universe, the universal wave function, evolves deterministically through time. There's no fundamental randomness, no genuine openness of the future. What we experience as random is just our subjective uncertainty about which branch of the wave function we're on. All branches exist in the four-dimensional structure, we just don't have access to the other branches. Even in interpretations where wave function collapse is real and introduces genuine randomness, it's not clear this gives us the kind of openness we think we experience. The randomness is at the quantum level, affecting individual particles or small systems, but our decisions, our choices, our sense of agency, these are macroscopic phenomena involving trillions of particles. It's not obvious that quantum randomness at the microscopic level translates into meaningful openness at the level of human choices. Moreover, randomness isn't the same as openness or free will. If my choices are determined by random quantum fluctuations, that doesn't make them free, it makes them random. I don't control randomness any more than I control determinism. So even if quantum mechanics introduces indeterminacy, it's not clear this rescues our intuitive sense that the future is open in a way that allows for meaningful choice. Now, I want to be careful here. I'm not claiming that free will definitely doesn't exist, or that our choices don't matter, or that we're just puppets acting out a predetermined script. The relationship between physics and free will is complex and philosophically contentious, and there are various ways to reconcile our sense of agency with physical law. What I am saying is that the block universe picture, where all of space-time exists as an unchanging four-dimensional structure, where there's no universal now, where past and future are equally real, is what our best physics suggests is actually the case. And this picture is radically different from our everyday experience of time as flowing with a special present moment and an open future. Let me give you another piece of evidence for the block universe: time dilation. This is a well-confirmed prediction of relativity that shows time is not absolute or universal, but depends on motion and gravity. If you travel at high speed relative to someone else, time passes more slowly for you than for them. This isn't just an appearance or a measurement artifact, it's real. If you take a round trip in a fast-moving spaceship while your twin stays on Earth, you'll actually age less than your twin. When you return, less time will have passed for you. You might have experienced 1 year while your twin experienced 10 years. This has been confirmed countless times in experiments with atomic clocks on airplanes, satellites, particle accelerators, and GPS systems. time genuinely passes at different rates for observers in different states of motion. Similarly, time passes more slowly in stronger gravitational fields. An atomic clock at sea level runs slower than an identical clock on a mountaintop because the gravitational field is stronger at sea level. Again, this has been measured and confirmed experimentally many times. These time dilation effects are incompatible with the idea of universal time flow. If time is flowing, how can it flow at different rates for different observers? What does it even mean for time to flow faster or slower? Flow relative to what? The block universe provides a natural explanation. Space-time is a four-dimensional geometry, and different paths through that geometry have different lengths as measured by proper time, the time experienced by an observer following that path. Just as different paths between 2 points in space can have different lengths, different world lines between two events in space-time can have different durations. There's no universal time. There are just various proper times measured along various world lines. This geometric picture of space-time, where time is just another dimension, where past, present, and future all exist equally, where there's no universal now, or time flow is not philosophical speculation. It's the picture that emerges from relativity, a theory that's been tested to extraordinary precision and has passed every test. Let me address one more aspect of our temporal experience: memory and causation. We remember the past, but not the future. Causes precede effects. These asymmetries seem to require a fundamental difference between past and future, a real flow of time from earlier to later. But again, these asymmetries can be explained without invoking a flowing time or a moving present moment. Memory and causation both have thermodynamic explanations related to the increase of entropy. Memories are low entropy states, structured information encoded in your brain. Creating memories increases the entropy of the surrounding environment because recording information requires dissipating energy. The fact that we remember the past but not the future is a consequence of the thermodynamic arrow. We can create records of lower entropy states, the past, close to the Big Bang, but not higher entropy states, the future, farther from the Big Bang. Similarly, our concept of causation that causes precede effects is tied to the entropy gradient. We identify as causes those earlier events that are correlated with later events in ways that involve entropy increase. But in the fundamental laws of physics, there's no asymmetry between cause and effect. The laws work equally well in both temporal directions, so memory and causation, while giving us a strong subjective sense of a directed time, are actually consequences of the thermodynamic arrow, which itself is a statistical phenomenon dependent on special initial conditions, not a fundamental feature of time itself. Now, having laid out the case for the block universe, let me acknowledge that this picture is disturbing and counterintuitive. It seems to deny the most immediate, undeniable aspect of our experience, that time flows, that the present moment is special, that the future is open. If physics says otherwise, isn't there something wrong with physics? Shouldn't we trust our direct experience over abstract equations? This is a reasonable reaction, but I think it's ultimately mistaken. Our intuitions about time were formed by evolution to help us navigate the macroscopic world at human timescales. They weren't designed to reveal the deep structure of reality. Just as our perceptual system misleads us about the motion of the sun, which appears to move across the sky, even though it's Earth that's rotating, our temporal phenomenology might mislead us about the nature of time. We shouldn't expect reality at fundamental levels to match our intuitions formed at macroscopic levels. Quantum mechanics violates our intuitions about particles having definite positions and velocities. Relativity violates our intuitions about space and time being absolute and universal. The deep structure of reality is under no obligation to match our everyday experience. Moreover, the block universe doesn't actually contradict our experiences, it just reinterprets them. You still experience a flow of time, a succession of moments, a distinction between past and future. The block universe explains why you have these experiences, because you're a four-dimensional structure with memory records and causal connections arranged in a particular way, and your consciousness processes this information sequentially, creating the subjective experience of flow, even though the underlying reality is static. It's like watching a movie. The film strip contains all the frames at once. Past, present, and future scenes all exist simultaneously on the strip. But when you watch the movie, you experience a flow, a progression from one scene to the next, even though nothing is actually flowing. The experience of temporal flow can emerge from the structure of static information being processed in a particular way. But here's where things get even stranger, because I've been presenting the block universe as if it's the final word on time, the ultimate truth that physics reveals. But it's not. There are deeper puzzles, unresolved tensions between different parts of physics, suggestions that our current understanding of time is incomplete. And exploring these puzzles will reveal that the situation is even more perplexing than the simple block universe picture suggests. In the next part, I want to explore the tension between relativity's block universe and quantum mechanics' apparent collapse of the wave function, the puzzle of why time has a direction at all if the fundamental laws are time symmetric, and the deep mystery of where the now comes from if it's not in the equations, because while the block universe solves some puzzles about time, it creates others, and the full story is more complex and more mysterious than I've suggested so far. So we've established that relativity gives us a block universe where all of space-time exists equally, where there's no universal now, where time doesn't flow in any fundamental sense. But this raises a profound puzzle. If the block universe is correct, if all moments exist equally in a static four-dimensional structure, then why does it so powerfully feel like time flows? Why do we experience a moving present moment? Where does the now come from? This is sometimes called the problem of the flow of consciousness, or the mystery of the present moment. And it's one of the deepest unsolved problems in our understanding of time. Because here's the thing, even if we accept the block universe, even if we acknowledge that physics gives us no evidence for a flowing time or a special present moment, we still experience these things. The experience itself demands explanation. Let me be more precise about what needs explaining. When you experience this present moment right now, as you're reading these words, there's a quality to that experience, a sense of nowness that seems undeniable. This moment feels qualitatively different from your memories of past moments or your anticipations of future moments. It feels present, immediate, actually happening in a way that past and future don't. Moreover, this sense of now seems to move or shift. A moment ago, you were experiencing a different now, perhaps the beginning of this sentence rather than the end. And a moment from now, you'll experience yet another now. So there's not just a sense of presentness, but a sense of flow, of the present moment advancing through time, of consciousness moving from one moment to the next. Where does this come from? If the block universe is correct, your entire world line, your entire four-dimensional existence from birth to death exists as a single, static, unchanging structure. All the moments of your life are equally real, equally present in four-dimensional space-time. So why do you experience only one thin slice at a time? Why does that slice seem to move? What singles out one particular moment as now? This is what philosophers call the problem of the passage of time, or the problem of temporal experience, and it's extraordinarily difficult to solve within the block universe framework. Let me walk through some of the proposed solutions and explain why each one is problematic. The first approach is to say that the experience of now is just a feature of how consciousness works, how our brains process temporal information. At each moment along your world line, your brain contains certain information, memories of earlier moments, perceptions of current stimuli, anticipations of future moments. The processing of this information creates the subjective experience of being at a particular now. In this view, every moment of your world line has its own now associated with it. When you're experiencing Monday, that moment along your world line contains the experience, now it's Monday. When you're experiencing Tuesday, that moment contains the experience, now it's Tuesday. Both experiences exist in the four-dimensional structure. You just can't access them simultaneously because consciousness is necessarily sequential. It's part of the structure of a moment that it experiences itself as now and other moments as past or future. This is sometimes called the many nows. View every moment is experienced as now from its own perspective, and there's no objective fact about which moment is the real now. Just as every place in space is here from the perspective of someone at that place, every moment in time is now from the perspective of someone at that moment. This solution has the virtue of being consistent with the block universe. It doesn't require adding anything to the four-dimensional structure, just recognizing that each moment in that structure contains, as part of its content, a subjective experience of being now. The flow of time is then explained as a structural feature of how moments are related to each other, not as any actual movement. But, and this is a big but, this solution feels deeply unsatisfying to many people, including many philosophers and physicists, because it seems to deny the very thing we're trying to explain. The experience that this moment, this now, is special, is the one that's actually happening. The many nows view says that all moments are equally now from their own perspectives, which seems to evacuate the concept of now of any real meaning. Moreover, this view doesn't really explain the experience of flow, of the now moving from one moment to the next. It just says that each moment contains an experience of being now, but that doesn't explain why it feels like the now is advancing, progressing, flowing. There's a difference between a series of static snapshots, each labeled now, and the dynamic experience of moving through those snapshots. Think of it this way. Imagine a flip book animation. Each page shows a slightly different picture, and when you flip through the pages quickly, you see apparent motion. The motion is an illusion, each page is static, and all the pages exist simultaneously in the book, but there's still a difference between looking at the book as a static object and actually flipping through it to create the experience of motion. The many nows view gives us the static book, but doesn't explain the flipping. It doesn't explain why consciousness experiences the pages sequentially rather than all at once, or why there's a direction to the sequence. These might seem like questions about psychology or neuroscience rather than physics, but they're actually questions about the fundamental nature of consciousness and its relationship to time, and we don't have good answers. A second approach is to invoke quantum mechanics and suggest that the now is related to the collapse of the wave function. In standard quantum mechanics, systems exist in superpositions of multiple states until they're measured, at which point the wave function collapses to a single definite state. Maybe this collapse is what creates the now. Each collapse is a moment of definiteness, of actuality, that divides past collapsed definite from future uncollapsed indefinite. This is an intriguing idea because it would give the now a physical basis rather than just a psychological one. The present moment would be where the quantum indefiniteness of the future becomes the quantum definiteness of the past. Time would flow in the sense that collapse events continually convert possibilities into actualities. But this approach faces serious problems. First, wave function collapse is itself deeply mysterious and controversial. Many interpretations of quantum mechanics deny that collapse is a real physical process in the many worlds interpretation. For instance, the wave function never collapses. All possibilities occur in different branches, and what we experience as collapse is just our branch of the wave function becoming effectively isolated from other branches. Second, even if collapse is real, it's not clear it happens in a way that could explain our macroscopic experience of a moving now. Collapse is typically associated with measurements or interactions which are happening constantly throughout the universe at all scales. If every collapse creates a now, then there would be countless nows happening constantly everywhere, which doesn't match our experience of a single coherent present moment. Third, and most fundamentally, this approach doesn't actually solve the problem, it just pushes it back one level. Even if collapse creates moments of definiteness, we still need to explain why consciousness experiences these moments sequentially, why there's a flow from one collapse to the next, why one particular collapse event feels like now, rather than all of them existing equally in the four-dimensional structure. A third approach, more radical, is to deny the block universe entirely and argue that the flow of time is fundamental, that the now is a basic feature of reality that our current physical theories fail to capture. In this view, the future genuinely doesn't exist yet, only the past and present are real. Time really does flow in some objective sense, bringing new moments into existence as it advances. This is called presentism in philosophy, and it has the advantage of matching our subjective experience perfectly. If only the present exists, then of course the present moment feels special. It's the only moment that's real. If the future doesn't exist yet, then of course the future feels open and uncertain. If the past has ceased to exist or exists only as records in the present, then of course it feels fixed and unchangeable. But presentism faces devastating problems when confronted with relativity. Remember that in relativity, there's no universal now. Different observers in different states of motion disagree about which events are simultaneous, about what exists right now. If only the present exists, and there's no objective fact about what's present, then there's no objective fact about what exists. Reality becomes observer-dependent in an extreme way that most physicists find unacceptable. Moreover, presentism seems incompatible with the basic structure of space-time that relativity describes. The equations of general relativity treat space-time as a single four-dimensional geometric object. They don't describe a three-dimensional present moment moving through time. They describe the entire four-dimensional structure at once. To make presentism work, you'd need to fundamentally revise relativity, and there's no empirical motivation for doing so. Relativity works extraordinarily well as it is. Some philosophers have tried to develop versions of presentism compatible with relativity, but these tend to be very complicated and ad hoc, requiring special structures or preferred reference frames that the theory gives us no reason to posit. The simplest interpretation of relativity is the block universe, not presentism. So we're stuck. The block universe seems to be what physics tells us is real, but it fails to explain our most immediate and undeniable experience, the sense of being at a particular now, the experience of time flowing from past through present into future. We have a deep tension between physics and phenomenology, between what our theories say and what we experience, and no fully satisfactory resolution. Let me make this even more puzzling by introducing another layer, the relationship between consciousness and time, because the mystery of the now is intimately connected to the mystery of consciousness itself. Consider this. When you experience a moment, you're not just experiencing a single instantaneous snapshot. You're experiencing a temporal duration what William James called the specious present, a short interval, perhaps a few hundred milliseconds to a few seconds, that's experienced as a unified now. When you hear a melody, you don't just hear one note at a time, you hear several notes together as a phrase, as a musical unit that spans time. This means that the now isn't actually instantaneous. It has a finite duration, but how long? And what determines that duration? Is it a feature of consciousness, of how our brains integrate information over time, or is there something more fundamental? Moreover, the contents of consciousness at any moment include not just present perceptions, but also memories and anticipations, connections to past and future that are part of the current experience. When you're conscious now, part of what you're conscious of is that this moment is connected to earlier moments you remember and later moments you anticipate. Your present experience includes temporal structure, temporal relations, a sense of being embedded in a flow, even though the experience itself is, in some sense, always now. This raises a profound question. Is consciousness itself inherently temporal? Does consciousness require flow, require a moving present, in a way that makes the block universe incompatible with consciousness? Or can consciousness exist within the block universe with the experience of flow emerging from the structure of static information, even though there's no actual flow? This gets us into what's called the hard problem of consciousness, the puzzle of why and how physical processes in the brain give rise to subjective experiences at all. And the temporal aspects of consciousness might be intimately related to this hard problem. Maybe we can't understand the now until we understand consciousness, and maybe we can't understand consciousness until we understand time. Now let me introduce yet another complication, the arrow of time and the puzzle of why it exists at all. I mentioned earlier that the fundamental laws of physics are time symmetric, they work the same running forward or backward, but that we observe a thermodynamic arrow where entropy increases from past to future. But this raises a deep question. Why did the universe start in such a low entropy state? The Big Bang appears to have been an extraordinarily special, low entropy configuration. All the matter and energy in the universe was concentrated in a tiny volume, in a very particular, highly ordered state. Since then, entropy has been increasing and will continue to increase until we reach heat death maximum entropy, complete disorder. But why this initial condition? Why did the universe begin in such an improbable low entropy state? If we're thinking about the block universe, where all of space-time exists as a complete four-dimensional structure, this question becomes, why does that structure have such a dramatic entropy gradient with very low entropy at one end near the Big Bang and very high entropy at the other end in the far future? This is one of the deepest unsolved problems in cosmology and statistical mechanics. There are various proposals. Maybe it's related to quantum gravity near the Big Bang. Maybe there's a multiverse where different regions have different entropy gradients, and we exist in one with a strong gradient because only such regions support life. Maybe there's some deeper law we don't yet understand that explains the special initial conditions. But here's why this matters for our understanding of time. The thermodynamic arrow is the only physical basis we have for distinguishing past from future. It's what gives us a direction to time, what allows us to label one direction toward the future and the other toward the past. If the universe had started in a high entropy state, or if it had no clear entropy gradient, we wouldn't have a clear arrow of time. So the fact that we experience time as flowing in a particular direction, with the past being different from the future, depends on the thermodynamic arrow, which depends on special initial conditions, which we don't understand. The directionality of time, one of its most basic features, rests on a mystery. And here's an even more troubling thought. In the far future, when the universe reaches heat, death, and maximum entropy, there will be no entropy gradient, no thermodynamic arrow. Does that mean time will cease to have a direction? Does it mean time will stop in some sense? Or will the four-dimensional structure still exist, but without any physical basis for distinguishing past from future within the high entropy regions? These questions don't have clear answers. We're at the limits of our current understanding, where cosmology, thermodynamics, quantum mechanics, and the nature of time all intersect in ways we don't fully comprehend. Let me now address a different puzzle about time, the relationship between time and causation. We normally think of causes as preceding effects. If A causes B, then A happens before B. This seems like a necessary truth, a basic feature of how causation works. But in relativity, the situation is more complex. For events that are close enough together in space-time that light could travel from one to the other, there's an objective fact about which happened first. These are called time-like separated events, and all observers agree on their temporal order. If A and B are time-like separated, and A happened before B in one reference frame, then A happened before B in all reference frames. This is what allows causation to work consistently. Causes can only influence effects at time-like separation. But for events that are far enough apart in space-time that light couldn't travel from one to the other, there's no objective fact about which happened first. These are called space-like separated events, and different observers in different states of motion will disagree about their temporal order. For one observer, A happens before B. For another observer moving differently, B happens before A. For a third observer, they happen simultaneously. This means that temporal order is not absolute or universal. It's observer-dependent for space-like separated events. Only for events that can causally influence each other, time-like separated events, is there an objective temporal order. This is strange enough, but here's where it gets really weird. In quantum mechanics, there are phenomena that seem to involve correlations between space-like separated events, correlations that can't be explained by any signal traveling between them at the speed of light or slower. This is quantum entanglement. And it's been experimentally verified countless times. When two particles are entangled, measuring one particle instantaneously affects the state of the other, no matter how far apart they are. This doesn't violate relativity. You can't use entanglement to send signals faster than light, but it does create correlations between space-like separated events that seem to require some kind of connection that transcends the normal causal structure of space-time. Some interpretations of quantum mechanics handle this by saying that the correlations are just built into the initial quantum state. The entangled particles were correlated from the beginning, and measurement just reveals that pre-existing correlation. But other interpretations, like certain versions of the collapse interpretation, seem to require some kind of instantaneous influence across space. If there are instantaneous influences, then the structure of causation might be more complex than the simple picture where causes precede effects. There might be connections in space-time that aren't mediated by continuous chains of cause and effect propagating at the speed of light or slower. And this would further complicate our understanding of time and its relationship to causation. Now let me introduce the deepest puzzle of all, the relationship between time and the laws of physics themselves. I've been talking about how time appears in our theories as a dimension in space-time, as a parameter in dynamical equations, but there's a sense in which time might be even more fundamental than the laws themselves. The laws of physics describe how things change over time. Newton's second law says that force equals mass times acceleration. It tells you how the velocity of an object changes over time given the forces acting on it. The Schrödinger equation tells you how the quantum state of a system evolves over time. Einstein's equations tell you how the geometry of space-time changes in response to matter and energy. All of these laws presuppose time. They describe temporal evolution, change over time, dynamics. But where does time itself come from? Is it something fundamental that exists independently of the laws, providing a stage on which physical processes play out, or is it emergent from something more fundamental? There are hints from quantum gravity, attempts to unify quantum mechanics and general relativity, that time might be emergent rather than fundamental. In some approaches to quantum gravity, time doesn't appear at the most fundamental level. Instead, it emerges from more basic structures only when you look at certain limits or approximations of the theory. For instance, in the Wheeler-DeWitt equation, which is an attempt to describe quantum gravity, there's no time variable at all. The equation describes a frozen universe where nothing changes. Time only emerges when you consider certain approximate solutions